Hey guys. How are you guys doing? Cool. Yeah, just my wife told me about some deal on Instacart. It was like you spend $450, you get $300 off. So I tried to order something, but I think we'll see if I get it. I tried to order some Chromebooks. Let's see. Okay, so I want to go over two things today. So just a show of hands. So hit yes if you have worked with this a little bit before and comfortable with these ideas, and hit no if you've never done anything like this before. Nice one. Have any of you worked with like Excel or spreadsheets? Do you have some experience with spreadsheets? Okay, nice. And some of you have not? Awesome. Okay, so I want to just show you a little bit of something you can do. Nice. Yeah, Google Sheets is really impressive. And it's actually gotten really good too, because they now can anticipate what you want to do sometimes and just like kind of do it for you. So I want to show you how to do some of these calculations for random variables, for discrete random variables. In particular, how to find the variance, and thus you can also find the standard deviation, and also how to find the expectation. So let me share my screen. Let me quit Safari here. Okay. Okay. And share screen. Great. Alrighty. So let's go to sheets.google.com. And I'll share this example as well. Let me go to Mr. Minsky Math. And I'm going to go here just because I already have it. And I'm just going to make a new one, though. How do I, let me just see here if I can make a new sheet. Okay. So we're going to go, I'm going to show you guys how to do this type of example. I'm just going to make a new sheet. Okay. So I want to show you how you can use Google Sheets, which is really similar to Excel, to avoid having to do some of the annoying stuff with the calculators and the annoying calculations. You can just do it and write it all on into the spreadsheet, and then they'll do it for you. And I'll give you the template so you can kind of play around with it. And I think I will also I didn't get to do this last year because I think it's really important to know how to use Google Sheets, especially if you want to do statistical analysis and stuff. This is not really kind of the main thing that Google Sheets is used for when you're working with data. This is more of like a calculation aid. But I'll keep, in the next few weeks, I'll think of something, maybe like a mini project that would be interesting for you guys to have some experience using Google Sheets. Okay, so let's use this to find the expectation of something that we already did, rolling the dice. So we write x, and then next column I'm going to write p of x. So these are this is the outcomes. This is the probability of a given outcome, and for the outcomes I can have 1, 2, 3, 4, 5, 6. And for the probability to, I'm going to write equals I'm just gonna, let's see if this works. 1/6, yeah, I'm just gonna write 1/6, 1/6, 1/6, and 1/6, and 1/6. And let's see, maybe here I can do something like center the number and maybe make it bold. And here as well, make it bold. And I'll just center it so it looks a little bit better. Maybe add a little border on this thing. What's that? Yeah, add a little border there. I don't know, whatever, that's fine. But, okay, so I have my x p of x. And now I want to do a calculation. I'm going to do over here x. I'm going to do the asterisk for multiply. And feel free to jump in if there's any. When I taught this last time, some of the students who had not, I'm not going to assume that all of you have seen this. So I'm just kind of starting this from scratch. So if you haven't seen, if you're not too familiar with Google Sheets or Excel, just jump in and ask me if there's any step that you're a little bit not sure where I'm going with it or what I'm doing. And I know it can be tough a little bit on the computer. And if you want, on the side, you can open up your own version of Google Sheets and try to just type this stuff in as I'm doing it as well. So over here, I want to calculate x times p of x. Oops. No, that's not what I want to do. X times p of x. Oh, sorry. And so here's where Google Sheets and spreadsheets in general are pretty powerful. So I can write equals, and then I can reference a cell. So I can do C3, and then I'm going to do times, which is the shift 8, which is the asterisk, times D3. Okay. And you see that comes out to 1/6. And the nice thing is maybe I want to I want to do the same computation, but I want to keep the same pattern going for each number below. So here's a really amazing thing you can do. What I would recommend, there's something called freezing, freezing an axis as you kind of, and you say, okay, well, I want the pattern to continue, but I want this quantity or this either row or column to never change. So in my expression, I want the column C and D, like where I'm getting X from and where I'm getting P of X, to never actually change, but the row number could change. So I don't actually need to do this here, but I put a $sign in front of the thing that you want to freeze. So I want to freeze the column. Okay, and then I'm going to go down and just you can drag and drop essentially, and you can see what this is. This is C4 times D4. This is C5 times D5, and so forth. That freezing thing is useful for, here you didn't really need to use it, but it's useful because if I were to do a new thing like extend it, let's see, let me think here. Yeah, if I were to do a new expression in a new column, it wouldn't shift the columns over, because sometimes it gets confused and say, oh, you want to use column C and D relative to column F. Now you want to move it to column G, so we got to shift over C and D to D and E, but this tells us to not shift over C and D. Okay, so and now at the bottom here, I'm going to just write this is equal to the sum, and it's going to actually, oh, here it doesn't do it, but it will tell me the sum from what do I want to do? The sum of F, and I can, yeah, I just do that. Just drag and drop F3, and you can write colon F8.
Yeah, I
now
don't think the numbers are quite right. You should double check the
yes.
formula for some of the ones below 1/6.
Yeah, let's take a look.
Because that one's correct. That one's not.
C5, D5, C6, D6. That should be 1.
Could you double click the 2/10 thing? Just so I
Yeah.
can see 6 times. Huh.
Okay, well.
Oh, I see the problem. When you use the slash formatting, it's not registering that that's a fraction. So
Oh,
it's 6 times. Yeah, you see what I'm saying? It's not multiplying it by 1/6. It's treating 1 and 6 as separate numbers.
I see. So should I change the formatting here to be
Yeah, change the formatting there by like select all the P of X ones and then click format and then change it to number.
Yeah, change it to fraction.
Oh, wait a second. Oh, oops, that's not what I wanted to do.
Yeah, so you
Um,
shift click.
yeah, shift click here.
And then shift click the bottom. No, you don't right click it. If you so you click that one and then go to the bottom 1/6.
Mm-hmm.
No, oops. Just go to the bottom 1/6 and then shift click that. So click the top 1/6.
Mm-hmm.
And then go to the bottom 1/6. Don't click it. Just hover over it with your mouse.
Oh,
don't
okay. Okay.
And then shift and click. There you
go. Nice. Okay, nice. That's a good. That's right. And then I can do
format.
Format.
And then number.
Oh, you know what? What if I had written in here instead? What if I just wrote it? Oh, it's a date.
Yeah.
Yeah, select all of them, go to format, and then number.
I see.
Because right now it's registering it as a date.
I think this is better.
Yeah, that'll work.
I don't know why it's doing that, but let's say Command C. Let's just do that. Wait, why is it doing that now? Why is the thing is 12/30? Yeah, I like that.
That is correct, isn't it? 12/30 is 1/6, right?
No,
that's not right.
That's not right. It's 5/30. All right, guys, we're having some. Okay, yeah. That's weird formatting because it's saying, huh? What formatting did I have here? I think I had previously just used the decimals. Okay, so let's say let's just use the format
number
or format number, yeah.
And
format
then there
number.
should be fraction.
Can I just do number?
Yeah. Okay, there you go.
Okay. Okay, so unfortunately, yeah, that's a little bit annoying. I would like to figure out how you could just like type in the fraction and have it work out. I don't know why it gave me such weird numbers there. But yeah, that's a good catch. And then maybe here, if you want to make it look a little bit prettier, you could. Well, I don't want to copy. I don't want to. Just want to select them. Format number. Let me see here, just something like that. Okay, just to make it like look a little bit cleaner. So that gives you your expectation. So here I'll write expectation. Okay, now let's calculate. Now let's use this to calculate our variance as well, and then we'll see some how the variances change when we. We'll see an example of how things change when we change up a random variable. So if you recall, to find the this is going to be x minus mu squared. This was the formula that we used. We took the distance from our output of the random variable from the expectation. I'm going to maybe just remind you here, we also called expectation, we use it, that symbol mu. So I'm going to reference that here. So this would be equal to, and this is where the freezing will be useful. So this is going to be equal to, in parentheses, C3 minus, and what should I subtract here if I want to subtract mu?
F10.
F10, perfect. And now F10, I want to, oh, no, that's not what I want. I want to freeze the F10. I want to freeze the F and freeze the 10. So that cell is frozen there. And as I'm going to copy and paste, the only thing that's going to move are these guys. The only references that are going to change are the things in the C column. But this is just frozen because I put the dollar signs. So it's always referring back to 3.5. And the formula says to square it to find the variance. Okay, so now let's just, you can hold this little guy, or if you want, you can hit Command C, Shift down until you get to the bottom there, and Command, oops, that's not what I want to do, sorry. Command C, going down, and then Command A. So just copying and pasting. Okay, and this, if you recall, this makes sense because we saw 1 minus 3.5 squared should definitely be the same as 6 minus 3.5 squared. So this is looking good. And now let's calculate our variance. So our variance is equal to, well, let's do the variance. This would be the expectation of this column. Maybe I'll make this in bold. So it's going to be, maybe I can make a new column. Let's see here. There might be a way to also write it out. You know, this is not the prettiest way to do it, maybe, but I'm going to do, I'm going to write a new column here, x minus mu squared times p of x, and then write out what I want here. So I want over here, I want to write this times p of x. Oops. This times p of x. Okay, and then I'm going to Command C. Here, Command V. All right, so I have these expressions here. And now the variance is going to be the sum of all of those. So this will be equal to the sum of G3 to G, oops, to G8. So we have a variance of about 2.91. And if we calculate the standard deviation, this would equal to, use the square root function. And as you type functions in here, there's a lot of functions in Google Sheets that are really useful. If you want to learn more about a function, you can hit this, yeah, where is it? Yeah, you can learn more. I guess square root doesn't give you much, but other, oh yeah, you can hit learn more. And it'll open up a really nice little, some examples and stuff. So this is a great way, you know, I'm not an expert at Google Sheets by any means. I know people who are really fast and can do incredible things very quickly on it. But you know, you don't need to have all of these things memorized. You can, if you ever work in this and you need to get better at it, you will over time definitely develop lots of shortcuts. But if you ever want to figure something out, you can take advantage of the help feature. It's really, really good. And it's the same in Excel. So this is just going to be square root of F12. Okay. Yes, Olivia, what was the last, are you asking about this one? Yeah, so this one I took I took what was in here and I just multiply the column B times the numbers times the probabilities to get the weighted value of column B essentially. And that's what we call the variance, to add all those numbers up. And then we take the square root of the variance and we get 1.7. Okay. So any questions on, maybe I'll make these bold. You can go with fancy with your presentation on it. And maybe let's see here. Border. Oh no, I'll do this. Okay. So that's how you can calculate the expectation and variance of a random variable. If you wanted to have a different random variable, like I have over here, I have the outcome x, the probability of x times p of x. I just set it up a little bit differently. Maybe it's better to write the variance right underneath it if you want, and then calculate the standard deviation. So this was the same sort of setup. And I think I did this for one of the Khan Academy problems. So you can use this. I'll post this template here, and you can mess around with it. But try to build it on your own, just so that you're comfortable with how we set it up. Are there any questions on how I did this, or any of the steps? I know maybe I did it a little bit fast, especially if you're not sitting by the computer next to me, it might be hard to see what I'm clicking and stuff. But any questions at all?
Could you show the standard deviation again, and how did you get that?
Yeah, of course. Are you okay with the variance step?
Yeah, I got that.
Okay, nice. So the standard deviation is just the square root of the variance.
Oh, okay, thank you.
Mm-hmm. Okay, so let's keep these numbers in mind, and then let me see here. Yeah, let me see if I can make a copy of this sheet. I'm going to duplicate the sheet. And so it's got the same setup, but now instead of doing 1, 2, 3, 4, 5, 6, let's do the random variable where all of the x's have been transformed. So now let's do, this time we're going to do the dice, the new random variable n, or x is the dice, let's say dice times 5. Let's just try that out. So everything on the dice got multiplied by 5. So this will be equal to 5. This one will be equal to 10. And I believe if I do this, I can extend the pattern without having to write it all down. Yeah, it just, if it sees a nice pattern, a nice sequence, it could automatically extend it for you if you click that little square and just drag it. So this is multiplying everything by 5. So what observations do we notice about the expectation and the variance and standard deviation? So first, what do we notice about the expectation?
It's gone up a bit.
Yeah, it's gone up a bit. In particular, compared to the previous one, it looks like it's gone up by a factor of 5. And that kind of makes sense because everything in this column got multiplied by 5. And then how about the variance?
It's gone up quite a bit.
Yeah, it used to be what, 2.9. Now it's 72.91. So how did it change compared to the previous one? If we look at the numbers.
Is that 25 times larger?
Exactly. So the variance is 25 times larger because we're scaling our random variable by a factor of 5, the things get spread out. If you're squaring the difference from the center, the distances get squared out by the square of your factor. And so when you take the standard deviation, that square goes away, and it'll just be 5 times the original standard deviation. So that's an important point, and I'm just kind of saying it, but make sure that you think about that the variance changes kind of like, it's very much related to those problems on SAT, whenever you have a circle or a triangle, and let's say you double the radius or you double the side length of a square, then the area changes by a factor of 4, but the perimeter only changes by a factor of 2. Or if you triple it, the area changes by a factor of 9, but the perimeter only changes by a factor of 3. So it's kind of the fact that the variance has a square in it, but the standard deviation is a square root. So it ends up also just being scaled by that factor. Okay, any questions on that idea? Can I ask a good question here? What does it mean to solve for the variance and standard deviation? What is it used for? After I go through this, Kalina, you'll see a little bit more of, I'm going to try to get to what we actually use standard deviation for. But the short answer is that it describes how spread out a distribution is. So if I just told somebody, hey, I'm working with a random variable with expected value 3.5, that's not super insightful. Maybe the expected value is 3.5, but maybe if you think of like some sort of game where every time you play, you expect to win $3.5, if it has a really high standard deviation, maybe this is a game where like there's a chance that you win $1,000 and there's a chance that you lose $1,000, and the chances is like 51% that you win $1,000 and 49% that you lose $1,000. In that case, the standard deviation is really high because the distribution is really spread out. Because you can either make 1,000 or lose 1,000 with different probabilities, versus like rolling a dice and saying like you get $1 for how many, what comes up on the dice. This is what this measures. That also has an expectation of 3.5. And if you look at the standard deviation of this, of the regular dice roll, it's about 1.7. So that's saying that like the spread is roughly between 1 and 6, which is kind of what we know about the dice roll. That's one interpretation you could have of standard deviation. And in terms of games, the example that I just gave is very much tied to the idea of risk. So if you are ever playing a game and there's some expected value and the standard deviation is very low, then that means that you're gonna expect, it's kind of like you're gonna expect to not be that far away from the expected value. But if your standard deviation is really high, like if your expected value is 3.5, but your standard deviation is 100, then you might range, when you do one turn of the game, you might range somewhere between negative 97 maybe and 103, for example. And lastly, just to kind of, you can compare this with no, maybe I don't want to say that. No. But yeah, it just has to do with the spread of the distribution. And we'll see in a little bit also how some other practical applications of it. Okay, let's do one more thing here. So this is the expected value, the variance and standard deviation. Here I multiplied everything by 5. But let's say I take the dice roll and I don't just multiply by 5, but I also add 3. I shift it as well. What do you guys think that will do to my expected value? It's just going to add 3, right? That it's just, if I add 3 to all these numbers, then if I calculate this, everything has a plus 3 in it, but all the px's have to add up to 1, so that's just going to add 3. what would that do to my variance? Does shifting my distribution or shifting my outcomes, like if I have my graph of my distribution and I just shift it over, what do you think that would do to my variance and my standard deviation? Excellent. It does nothing. So that's a really important idea that we're going to apply a lot. When you shift a standard, when you shift a distribution by a constant amount, you shift the entire distribution, the variance and the standard deviation don't change. Does anyone see from the formula why that, like an argument why that you can make that would justify that just from the formula?
The average is shifted the same amount as your x value, so it's not going to be a different output.
Awesome. Yeah, the x minus mu thing, the x is shifted, the mu is also shifted. Subtracting them, there's no difference. Excellent. So yeah, let me just see if that works. If I change this to 8, and then what would this be? 13. Let's see if Google Sheets can continue this pattern. I think it can. Yeah, it does. Sweet. So observe our expected value changed, but our variance and standard deviation stayed the same. And that really captures the idea of that the fact that the standard deviation measures something about how spread out your distribution is, doesn't care where it's located. It just wants to know how far away things are from the average. That's it. Okay. What do you guys think? Any questions? Looks good. This is going to be really helpful. I'm going to assign some questions where you will analyze different games of chance and to see if they're worth playing. And you can do these questions just by plugging in, and you can get the standard deviation, the variance, and the expected value just by plugging in different probabilities into this. Okay. Yeah, and I think in this example, this was for one of the questions in the Khan Academy. All right, so let's shift gears a little bit. What else could I say here? Yeah, let's shift gears a little bit. And I'm going to stop the share here. Any last questions before? Please hit yes if you felt, just to kind of get a sense, hit yes if this all kind of made sense and you followed what the calculations are and you felt comfortable with the Google Sheets. And hit no if you felt a little shaky with Google Sheets and you kind of want some more practice. Wonderful. Okay. Well, looks like a lot of people are feeling pretty good about it. Awesome. All right. So let's stop the share. Oh, the new share. iPhone, iPad, VR. Something here. Okay, and I'm gonna do a new share right here. iPhone, iPad, VR, play. Share this guy. So new share. Okay. So we're gonna go and now start. We've learned a lot about probability. We learned about random variables. Now we're gonna get into some basic ideas in statistics. And some of you might have even seen these ideas before as well. This is going to be intro to stats, the normal distribution, and the bell curve. So I kind of talked about this last time. One phrase, just a curiosity, how many of you have seen the show, heard of it, X-Files? Do you remember the main slogan from that show? Does anyone remember the tagline or whatever there was always a phrase they had. In part of the title, I think. This is I think before your generation, but it was when I was in like growing up. So X-Files, they always have the saying, the truth is out there. They were like hunting extraterrestrials and ghosts and whatever, mostly extraterrestrials. I don't even remember too many of the episodes. I think I should go back and rewatch some of them. So I find that this idea really helped me understand better why we do statistics. So one common problem that a statistician might try to answer is they want to understand something about a population. So a possible question is, so question, what is the average height of all giraffes in Africa? So you have a statistician starts with a question about a given population. So statistics tries to answer a question about a population. So one type of question you can ask is, what is the average height of all giraffes in Africa? Now, what do you guys think? Is this is there a correct answer to this question? Is there like a true factual answer? Quentin says yes. A few, Lydia says yes. Awesome. Let me see. I'm just gonna ask Jackson. You said that there's a true actual answer. What would we need to do to get that exact answer? Or anybody? You can just hit spacebar if you want to jump in. If you want to get the exact answer of this question, what would you technically need to do?
You need to ask.
Yeah, go ahead, David.
Measure the height of all of the giraffes.
Exactly.
Add it together and divide it.
Nice. Now, is that something that we would have the resources to do?
Probably not.
No, maybe it's possible, but most likely we would need to take a subsample or a sample from the population. So what statistics tries to do is instead, so it might not be feasible to measure every giraffe. And of course, this is like a great example of something that's feasible. And maybe you could spend your whole life going. Maybe, I mean, sadly, there might not be even that many giraffes. That's the sad part. So I don't know. I don't know. I don't know what the current giraffe population is in Africa. Might not be feasible to measure every giraffe. Instead, maybe you go to a few national parks there, and just like see if you spot a few giraffes and take 100,000. Okay, that's not too bad. That could be doable. Might not be feasible to measure every giraffe. Instead, you can take a sample. You know, the reasons it might not be feasible, you might not know where every giraffe is, so it might be hard to know how many there are. Another reason that for example, Apple, when they do manufacturing, and Samsung also to some extent as well, or any company, when they do manufacturing, there are certain things that you want to test, but you can't. If you did it every time on every single device that you produce, it would just not be very efficient. For example, Apple, when they make a screen, they might want to test to see the durability of the screen that they make. But if they just like did a shatter test on every single screen that they make, that would really not be a good idea. So maybe they do a shatter test on a sample, like 1 out of every 100 screens that they make, just to make sure that the quality is still really good. So these are times where we might not want, so sometimes it might not be feasible to measure the entire population, and sometimes you might not want to measure the entire population because sometimes measuring something requires a lot of resources or kind of defeats the purpose of even making the object. So might not be feasible to measure every giraffe. Instead, we take a sample. And these ideas are really simple. I'm just kind of going through it carefully because I think it's important to use the right language when talking about statistics. Instead, take a sample or a subset from the population. Okay, and so the idea is that and calculate something we call a statistic So in this case, it would be the average of our sample, or the sample average. And use it to estimate the value of what we talked about with the X-files, the true parameter of the population. Okay. Okay, so this is essentially oh no, white rhino. Are they only in zoos, or are there none left?
There's actually more than I thought. There's like 19,000. That's a good
Oh.
amount.
Oh, wow! In Africa?
After more than a century, blah, 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 they're now classified as near threatened species in protected areas and private game reserves.
Okay. Wow. Yeah, my wife's nephew, well, this is not a rhino, but he went to the zoo and he saw people feed a hippo, which I'd never seen before. That's oh, there's two different types of rhino. I see. One of them. Okay. Oh, interesting. Northern white rhino. I'll take a look at that later. So yeah, we're going to try to use our sample average to say, you know what, based on this sample average, we're going to estimate that the true number, which does exist, it's not like it's an imaginary number, it's going to be in some interval. We just don't have enough information to tell you exactly what that parameter is, but we have a good likelihood. We're gonna give you we're gonna give you an interval with a really good likelihood that your number is the true number is somewhere here, and that's makes some sense. And in general, if you want to be more accurate, where with your estimate, what do you think you should do?
Measure more rhinos.
Yeah, or yeah, measure more giraffes here. Yeah, increase your sample size. So increasing your sample size will give you better accuracy for your estimate. And so so these terms, parameter is to population, like statistic is to the sample. So that's an important. Oh, so be careful. The term sample space, I think it might have. Yes. So sample space is technically would be like all possible things that you can sample from, maybe like all possibilities. And the sample is a specific. When we talk about sample and statistics, it's a specific subset of your population. Okay, so I just want to mention this fact. Um, uh, uh, Population and sample could always be relative. It's up to you as a statistician to decide is up to the statistician to decide. So, for example, if I wanted to, let's see, so let's say measure the average height of every student at High Tech High. In some sense, depending on what you are interested in, right? You could consider High Tech High to be its own population, and maybe just pick a sample of a few students from High Tech High to try to answer this question. Maybe you're not able to find the average height of every student. But at the same time, if you want to answer the question about like maybe what's the average height of high school students in California, and you happen to have a bunch of data from all the students at High Tech High and maybe a few other schools, in that case, the average height of every student at High Tech High would be part of a sample. And the overall population would be the all students in the US or maybe all students in California. So it's really, the idea here is that it's really up to whatever, it really boils down to what question you're asking to determine what is your population, and then you can go and figure out what sample you should pick. And in general, we're not going to do too much discussion about this, but in general, you want to pick. A statistician always wants to pick a random and representative A really simple example is related to the election is if you wanted to find out how people were going to vote for the presidential election in Florida, you wouldn't want to just ask people in other states. You want to ask people in Florida. You maybe ask a handful of people, and you wouldn't just ask people in Miami, but you might want to ask people from all different parts of Florida. And you could figure out different ways to make it representative and also random. Does anyone know why you shouldn't, if you want to, maybe you guys have done more reading about this, but does anyone know what are some kind of ways that polls where they ask people like what they want to vote could sometimes be incorrect or be misleading? Nice. So there's something we call bias, which is creates a source of error in our prediction. But what's an example? Nice, Adam. Yeah, exactly. They can poll only certain people. That's a really good source of bias. So maybe they're only polling like at a university or something like that, or only polling at a supermarket. Like, only the people who are shopping. Oh, okay. Yeah, I just let him in. Yeah, one other interesting source of bias in polls, and they try to avoid this, but it's like the way you ask the question. If you can ask questions in certain ways to like persuade people to give a certain answer. Like you can say, "Oh, do you think the pandemic was handled terribly?" That's an easier question to say like yes or no than a slightly different phrasing. So there's all sorts of examples of bias that can be introduced. Okay, so are there any questions on these ideas? The most important thing I would take away from this is that the parameter that we're trying to figure out, it's a real true number. It exists. And we are only using estimation of a sample by calculating a statistic to estimate where that true parameter is. For some reason, that idea tripped me up when I was taking stats, because I thought for a while, because we're going to tie this in with probability and stuff, and I thought like, well, I understand the outcome of rolling a dice, like that's 1/6, 1/6, 1/6, but the outcome of who wins an election, how can you say that that's going to be like 40%? That doesn't make any sense. Like, how do you know? Like, that's how can you say that? So we'll kind of justify that later in the course. Okay, so now let's talk a little bit about the bell curve. It turns out, and we'll discuss this in a future class, but it turns out that a lot of things like height, weight, a lot of quantitative things that you can measure for a population will be spread out, will be distributed like a bell curve. And the formula for the bell curve is P of x equals e to the negative x squared. And I'm not assuming that you all have taken pre-calc or anything like that, but so this is not super, you don't need to know this, but it's nice to see if you have taken pre-calc. Does anyone know, so E is, you might not have seen E. E is just a number, it's like kind of like pi. It's like 2.718 and it continues on. It's roughly 2.718. And e to the negative x squared. Can anyone tell me what happens when x is equal to 0? What does this function look like? It's just 1, because anything to the 0 power is 1. And what happens as x gets larger? Like if x is equal to 1, then 2, what happens to the number to this function? It goes, Quentin, why does it start to go down?
Because it's a negative exponent. So as you increase the value, it gets lower.
Excellent. And then what about if you plug in negative x? What happens there?
Negative x.
Like you plug in, sorry, if you plug in like -1, 2, -2,
Oh.
-3.
It would still go down because it's squared, so the negative goes away.
Exactly. So the negative inside the number goes away because you're squaring it, but the exponent still has that negative out there. So it turns out that this number has a maximum value at the origin, and it tapers off really quickly as you get larger and larger. And you can explore this on Desmos if you're curious. And it turns out that there's some other numbers that you need to like, I think it's like, there's some numbers over here. There's some, I forgot exactly, I think it's like 1/2 pi. There's some numbers you need to plug in to make sure that the area under the curve is equal to 1. Because remember, for a continuous probability distribution, we needed to make sure that the area under the entire curve represented the entire probability. So the total area is 1. So there's a distribution called the standard bell curve, or the standard normal curve, or standard normal distribution. So a continuous distribution is called normal if the formula. Now this is not the only bell curve you can draw. Just like there's lots of different parabolas, but all the parabolas, they have the same parent function, y equals x squared. But you can make the parabola skinny, wider. You can move it up or down. You can flip it. So similar like this, we can take these bell curves. We can make them a little bit skinnier. We can move them to the left or right, and we can move them. We can't move them down, but we can move them left or right, and we can make them skinnier or wider. But they're always going to have this bell shape. And it's called normal if it has the bell shape, or if it follows that pattern. If it y equals e to negative x squared as its parent function. This is just a fancy way of saying it has a bell shape. And in particular, just like it was helpful when you do the stuff with parabolas, it's really important to know how y equals x squared looks like. When you do stuff with like different logarithm curves, for example, you really got to know what y equals log of x looks like. When you do like exponential stuff, you need to know like y equals 2 to the x. You really need to know how the parent curve looks like. The most basic parent curve is really important. And so the same thing applies here. The standard normal we write it, we have a special notation for the normal distribution. We write it n, 0, 1. Is the bell curve with center equal to 0. This is, in other words, saying mu equal to 0. And standard deviation is equal to 1. This is sigma is equal to 1. And in general, you can have other bell curves n mu sigma gives all possible bell curves. But the cool thing is, if you understand how the bell curve, if you have access to information from the bell curve, just the most basic one that's centered at the origin, then you can figure out by doing a simple transformation all the information you might want to figure out about the other bell curves with different average values and different standard deviations. Okay, so now let's go to we'll go here, Z table. Okay, so this is, I'm going to drop a link and I'll share this link in the chat as well. Okay, so please visit this website, Z table. And Z table, what it's a graph of is the standard normal distribution. It's got a bell curve, the middle part's the bell, and it's got those tails on the left side and on the right side. And this is a probability distribution. What's useful about this table is we can answer questions like this. So let's say we have the standard normal distribution, and Z, we usually use the letter Z, is we write Z is normally distributed with mu equal to 0 and sigma equal to 1. Or instead you can say follows the standard normal distribution. There's a few ways of saying it. So if we look at this table, we can answer questions like this now. What is the probability that Z is less than 1? So this table is a little bit confusing to read at first, but I'm just going to draw the picture of what this represents. I have my bell curve, and because I know it's the standard bell curve, I would technically know exactly what it looks like. I know the exact formula for it, and I'm going to use this. This is the origin where it's centered, and I'm going to go to the number 1. Now I want to know the area of the region that's to the left of the number 1. And to get that, I'm going to look on my table and I'm going to look for a Z value of 1, of positive 1. And this table is a little bit confusing. Let me just so the z value or the cutoff value is z equals 1. I want everything to be below. I want to see what's the likelihood that I guess observe something below the number 1. So let me do a new share here, desktop 2 and share. So the probability of observing something below 1, the numbers in here, if you notice, they start off really low, and they represent the area to the left of a given z value. So they start off really small, and as you go from left to right and down, they keep going up and up. And this table is a little bit weird. These are the z values, negative 3.4. These are the values kind of on this axis over here. But these numbers are further refinements of that value. So this, you would read this one as negative 3.41. This would be negative 3.42, and so forth. So really, kind of as you're moving your z value along here, what's happening is you're kind of wrapping, your probability values are wrapping around this table like this. So in particular, when you get to 0.0, you're in the middle of your bell curve. What's the chance that you're going to be to the left of the middle of your bell curve? It's 50%. Yeah, and here it's and these are negative, so these are getting less negative actually. So you have to be careful. So that's actually, I misspoke there. It's actually wrapping around like this.
Wait, really quick, could you explain those decimals again? Like, for example, if you were to go to negative 3.4 and not the like decimals in the table, the ones next to that z value. Like if I were at negative 3.4 and then 0.01, would that be negative 3.401 or negative 3.41, I guess?
Exactly, yeah. It's like you're adding, this is like a further refinement of the negative 3.4.
Okay.
This is just the 100th place. So this column tells you the 100th place of your number, and this is just tells you the first, the ones and the 10th place. And the number inside the table, that represents the gray area, the probability. And then the table as you get larger and larger, this bell curve has total area is equal to 1 because it's a probability distribution, it has to have area equal to 1. And so as you get larger and larger, eventually you get really close to 1. So what did I ask? What's the probability that z is less than 1? So you just go to 1, and in particular, it's not just 1, but it's 1.00. So that would be the first term over here. So that tells you that there's an 84% chance that if you were to pick something from the standard normal bell curve, you would pick a number that's less than 1. So this is going to be oops, I'm going to write it in black, and I'll 0.8413. What do you guys think? What's the probability that, and you guys can just message me, what's the probability that I pick a number that's less than negative 0.42? What's the chance that if I'm drawing from this bell curve, what's the chance that I pick something that's less than negative 0.42? Nice, we got one answer so far. Oh, that's good. Oh, no. Oh, my bad. Sorry, Quentin. That's right. Nice, Lacho, excellent. Yeah, you go, this is the point, this is a 200ths column. So you get a negative 0.4, and you go to the 200ths, and you just see where they intersect, 0.3372. Excellent. Okay, so we're going to reference this a bunch, so please have it open as we're working on these.
Sorry, I'm a little confused. Why does the table end at 3.4 and positive 3.4 and negative 3.4?
Good question. It's kind of arbitrary there. The idea is that you see like at 3.4, it's already 0.9998. So it's like one interpretation of that is to be like in the standard distribution, standard normal distribution, if you're over 3 units to the right, the chance of observing something like that is like less than 1 in 10,000. So it's just like really, really rare. I don't have the curve anymore, but the tail in the middle, there's a good amount of probability, but because it's like an exponential curve, as you increase the number even just a little bit, like even 3, right? It gets really, really tiny. The tail gets really thin in the standard normal curve.
All right, cool. Thank you.
And I think maybe the reason they do 3.4 is because it's like the 1/10,000th. So you could technically keep going if you want to model really rare events. There's no limit to it, but for all practical purposes, you generally stay within like negative 1.5 to 1.5. Okay, so what this tells us, and this is kind of going back to what Kalyana asked about the what is the standard deviation good for? So in the bell curve, in the standard bell curve, the unit 1 is the standard, like 1 is the standard deviation. So we have something called the rule of thumb. Let me share my screen here. Oh, sorry. So this is the bell curve rule of thumb. So if you have a distribution that follows the standard normal distribution, and in later class we're going to extend this idea to discuss not just the standard normal distribution, but really any bell curve. For example, like giraffe heights. Giraffe heights might be distributed with an average height of maybe 10 meters and a standard deviation of 2 meters. So there's some bell curve that you can draw that's centered around 10, and you can kind of expect giraffes between 8 and 12. That could be a good approximation. And we'll figure out how to use this table to answer questions about giraffes. We can use this table to answer questions about rhinos, and we could use this question to answer table to answer question about like test scores and stuff like that. So there's a lot of applications of this idea. But let's just do that for now to get a sense of the standard bell curve. What are the probabilities underneath it as you kind of go away from the origin? So here's our bell curve. And I probably should draw it a little bit better. Let's erase this here. I'm going to draw it like this. It really supposed to get small. Okay, so if it's one unit away, and keep in mind this is for the normal distribution, this is 1 standard deviation, one sigma. This is the graph of n 0, 1. And I can do this later. We'll do the similar thing, but with instead of 0, 1, we'll do mu and sigma. Mu and mu plus sigma. But we saw that if you look at one, yeah, exactly, Chester, that's right. Margin of error is very similar to the rule of thumb. If we look at the z-score, so the z-table, we see that 84% of the data is less than 1. So if I highlight this area, this is 84%. And then if I look at -1, can you guys tell me what percent of the area is less than -1? Let me see here. -1, yeah, about 0.1587, so about 16%. So I'll put that in green over here. So this part is here, and then that part is here. So that's 16%. Okay, so therefore, if 16% is the tail to the left, and 84% is the bigger tail from +1, what is the area of the region in the middle between -1 and 1? Or what's the percentage of the total area that goes in there? It's going to be 68. Exactly. Nice, Quentin. Are you guys okay with that? If you subtract the two pieces, the big piece minus the small piece, what you're left with is the middle. So this is one important thing. That's we say that there's a 68% chance, if you're drawing something from the standard normal distribution, that you get between one, you're going to be at least no more than one. There's a 68% chance that you'll be no more than one standard deviation away from the from 0, because 1 happens to be the standard deviation. So this has a 68% chance. So most of the data will be within -1 and 1. Let's do something really similar between -2 and 2. So all the way between -2 and 2, I'll just kind of draw it out. So let's see if we can figure out this number. Do the same thing. I don't know why. Draw it really quickly here. And also, by the way, this tells us that down here, it's going to be 34%. So this is 34, because it's symmetrical. So this is 34. So we get some nice information like that. Okay, what's to the left of 2? If we look at 2.0, what number do we get? I got about 0.98. So that's including everything up to there. And if we look at -2 on the table, -2.00, we get 0.02. So this part is 0.02. So that tells us that the middle region is actually going to be quite big. It's going to be 96% of the data. It falls into this between -2 and 2. So this is 96. And what do we have? We had 34. 96 divided by 2 is, well, you don't need to actually break it up, but the idea is 68% of the data falls within -1 and 1. 96% of the data falls between -2 and 2. And therefore, if you ever measure something that is more than 2 standard deviations away from the origin or from the mean, then that tells you that it's a really rare event. So generally, 2 standard deviations below and above your average value. In this case, we're just doing the standard normal. So 2 standard deviations, between -2 and 2, which is 2 units away from 0, is what will capture most of your data. And so that's called the rule of thumb. The fact that 68% of the bell curve is between -1 and 1, and 96% of the bell curve is between -2 and 2. And from there, you can figure out all the other pieces that you might want because of, this is 96. Let me erase this. This is 34. what's going to be left over? If this is 96, if the total is 96, if you divide that by 2, that will be 48. So this will be 14 here and 14 here. So these are good ways to kind of get a quick estimate. If you know these numbers, you can get quick estimates on like what's the chance of observing some outcome in a given interval. All right, guys, I'll post some stuff from Khan Academy so you can start working on the next homework. Next class, we'll start talking about z-score, which is just generalizing this idea. Instead of using, instead of talking about mu equals 0 and sigma equals 1, we can do problems with other mu's and sigmas, like giraffes, elephants, and all we do is really simple. We're just going to transform that mu and sigma. We're just going to move it to the standard bell curve and then work with the standard bell curve. So every problem that you see that involves a normal distribution, you're essentially just turning it into one of these problems so you can use the table. All right. I hope you guys have a great weekend. Are there any questions so far?
Just a minor curiosity. Does the word normal have anything to do with geometry normals, or is it just because most things fall into that distribution? So it's normal.
Yeah, very good question. Normal, were you referencing like the fact that normal means like length? Or no, normal could be perpendicular or?
Yeah, normal is usually the direction like light would bounce off something.
Yeah, okay. It's not, yeah, it's really funny. Normal has like a lot of different definitions in math. I think this one is called normal just because it shows up a lot in nature. Like there's a theorem that we'll study called the central limit theorem that explains why it shows up. It's like a natural phenomenon. So it doesn't really have anything to do with being perpendicular or like a magnitude or anything like that. It's just just another time that the word normal shows up. But I might not be. Yeah, I don't know. That's my guess. I could take a look though. I'm curious as well if that has anything to do with it, but I don't think so. And I'll also later share some really cool visualizations because it's really incredible why this shows up, why this specific curve shows up in nature. It's like it's almost as important as like the law of gravity. All right, guys, have a great weekend.
Thank you, Daniel.
See you, Quentin. See you, Colin.